Start again. Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. This afternoon, we have Sophie, Marques, and Leandro Boonzaaier with us. And I won't read the title because it might scare you away. No, thank you very much for coming. Let me just briefly introduce the two speakers. Sophie did her PhD in between Padua and Bordeaux, after which she spent a couple of years at the Couronne Institute in New York before coming back to South Africa as a postdoc, and then since 2019 as a senior lecturer at Stellenbosch University. Yeah. Leandro is not a mathematician, he's a theoretical physicist, who studied in Stellenbosch, and for several years he was affiliated with the Stellenbosch physics department, and then he embraced a career in the private sector, let's put it that way, but still holding links with the Stellenbosch physics department intermittently, I guess. Yeah. So, Sophie and Leandro, I'm not sure how you want to play this, but it's now over to you. Yeah, thank you very much.
I will just say a few about who is our co. Not aware. The support of NITheCS, and it's a bit of a different way. Mathematics is accessible to all and useful to all, and not majoring in math or doing research in mathematics. So to find us is like type this word. I don't think that exists, so only us should appear. And you find us. If you wish to help us with a project, you are welcome to send an email. And you can get in touch with us. Either you can contribute or you can contribute or write a column or like to do, please ask us and send us an email and get in touch with us. So the title of the talk today is what are the possible near-field structure one can define over the multiplicative group near a ring. So we will keep it very basic. Probably you know everything I will tell you, and it seems basic, but it's quite subtle. So keep up with it. So you all know the natural numbers, the integers, the rational, and the real algebraic and the real. Everything starts with 1. 3 billion years ago, we have a start of the first 1 appearing in some bones, but we were starting to count at the time. And if you think about the concept of 2, it's just a name to something that you can figure out from your brain by associating patterns somehow. You think as both that 2, you think of it as a 1 plus 1. And you associate those 2 things together. You say that they are equal, but just the explanation of what 2 is. When you have 3, now there is like a little problem. You can get 3 in very different ways. You can get 3 like 1 plus 1 plus 1. You can get 3 like 1 plus 2. You can get 3 like 2 plus 1. And you can get 3 like writing it for mathematics like that. So this is called the associativity property. There is no point in time where you will add 3 numbers in your head at the same time. You will always choose 2 numbers and then add another one to it. And there is 2 ways to do it, and the 2 ways coincide. And that's a very important property of your addition. So you can understand now that actively you continue this process and you will define what is known as the natural numbers. Okay. So the natural numbers were discovered much later time, like properly formally defined, when the first time that one was kind of thought of. So it takes a long time for mathematics to formalize. The 0 symbol had a nice story because it had a lot of controversy the first time that it appears. People say, why would you give a name to nothing and you would make it into a mathematical symbol? And it took a long, long time to convince that 0 was kind of an important mathematical formal symbol. And now we know that it's absolutely revolutionary, not only for computer system, but also for writing number effectively, because the poor Roman system of number was not very efficient. So in mathematics, we see 0 as the special element, such that if you add it to anything, you get the same thing. This is referred as a 0 element over set as well. So the negative number, it's a bit of the same story. People didn't want to accept them for a very long time because you cannot kind of think of a negative number in a concrete way. I can think about 1 bottle, 2 computers, but you cannot think of -1 bottle. So it was another way of thinking which was required to accept negative number. But when society started to collide together, negative number gained on their popularity because of tax and debt. So now you needed negative number to count. And that's how they were accepted by society. So the concept of -1, it's like the concept which validate the string of symbol that I wrote here. -1 plus 1 is the same as 0, is the same as 1 minus 1 plus -1. Once you know what -1 is, then in the same way you did for natural number, you think of what -1 plus -1 will mean, and you call it -2, etc., and you define all the integers like that. So when you want to add now positive number or a positive and negative number together, you can pair the plus and -1 together, they give you 0. You know how it acts on the sum, and then you get a string of 1 and a string of -1, and you know what to do because you know what it means. The addition is commutative. That's important. It means that if you add 2 numbers, it does not matter in which order I give you the 2 numbers, it will give you the same thing. Rational numbers were invited in the 6th century. I see them as a little more continuous than the real number, but not quite continuous as we wish. But like, I put that because it's very unclear what I'm saying here. I'm not being formal today. I decided not to be. And so you think of a unit, a way to think of the rational number. Probably it's not the only way. You think as 1 as a unit that you can cut. And then you will take portion of that unit together. If you think of it like that, then you know what to do. Once you have the same cut of pieces, you can just add in the same way that you always add natural number. So if you wanted to add natural number together, let me just see where I am. If you want to add a natural number together, it's like a, oh, not yet here. So sorry, I'm a bit red. So natural number, rational number start filling up the real 9, and natural number are rational when you decide that n over 1 are conceptually the same, almost the same. So rational number make the equation px minus q have a solution. So once you want to add rational number, you combine the sign into the denominator, into the numerator, and then you choose the cutoff length that is common to the two, and then you use the addition which you define for integer, and you add things together. And you get the normal addition that we all know of rational number. For a very long time, Pythagoras thought that rational number were the only number which filled up all the line, and that there was no over number, and they were enough to describe every possible number. But then Hippasus was the first person to recognize the existence of irrational number. So one of the irrational number, if some of you have seen it in class, would be that square root of 2 is an irrational number, and there is like a famous proof for that. Or square root of 2 is understood as the symbol, which is the positive number plus order for the equation x squared minus equal to 0. So how to think of irrational number coming from rational number, because if you follow what I'm trying to do, I'm trying to tell you that everything comes from natural number. And once you understand the natural number, you can kind of understand everything. And the fact is that every real number is a sequence, the limit of a sequence of rational number. And here we finish the continuity because we are filling up all the gaps. Then we thought we were done. No, there is more. There is complex number, but this took lots of controversy. And Descartes was the first to emphasize the imaginary nature of numbers. And Cardano conceptually made sense of complex number. And later, on the 18th century, Gauss consolidated Cardano. But this is very, you can think about it. So here you need a bit of even more abstraction, like probably what people thought of abstraction to come from natural number to negative number. You reflect on the equation x squared plus 1 having no solution, but then you decide, why should it have no solution? Let's imagine it has a solution. And again, I'm being very, very informal here. So we define a number to be a plus ib, a and b real number. And you can conceptually understand what that notation means. By adding, for instance, more information, you will say that this thing is equal to 0 if A is equal to 0 and B is equal to 0. And then you define the addition. Again, keeping in mind how the addition was defined in R and transferring it. So now, how can we think about the multiplication of integer in terms of addition? We all know that, but I will repeat it anyway. So n times n, if there are both natural number, can be understood as m plus m plus m, so repeated addition n times, or n plus n and n, repeated addition m time. And you see that I can rewrite this observation like that, which is referred also in a special case of the distributivity problem. So then if you want to do integer, you probably already know what to do. You take care of a sign, you put it in front, and you just do the multiplication of the integer, of a natural number. And then if you want to understand the multiplication of a rational number, same thing. You can think of your cutoff, common cutoff for the two number, and then just repeated addition of a rational number. And if you want to understand the real number multiplication, you take a representative sequence which tend to that real number, to each of them respectively. The multiplication would just be the limit of that. And for the multiplication of number, you have to have reflected a lot on what you have observed before and see that there was some kind of distributivity, and you just apply that same kind of distributivity, remembering that I squared is equal to -1, and you get a definition multiplication. So the conceptual understanding of the addition of a natural number induces the addition and the multiplication, real number and complex number, in a kind of continuous way. We'll leave the continuity, maybe there will be more than that, but if we keep the continuity, you will get the multiplication like I explained to you. Another thing that I want you to realize is behind every single of those systems, there is kind of an equation which motivated that you couldn't solve, and now with a new system, you can solve it. Another thing I want you to understand is that conceptual understanding, even a single concept like the one, evolve as your knowledge grows. So you can think you understand one, but I did spend a lot of time trying to understand one, and I realized that I don't understand one. And I probably cannot understand one. The reason is that if you define something, you need to define that thing with something you have understood before. But it's like the egg and the chicken, who comes first? So at some point you will have one notion which should come first, and I think natural number, probably integer, are one of them. And we need to be open-minded. You might think that something is completely useless, but maybe you don't have an understanding which permits you to see that it could be useful. So you need to keep at it, try to understand it, and understand if it's not useful, you need to understand why it is not useful. And you need to understand why something is. So why are Z, Q, R, and C rings? So there are rings, unitary ring, actually. There are rings, so if you go back, I had two operations on each of them, the addition and the multiplication. The addition was associative, commuting. It didn't matter which order I took. I had this 0 element, and I had this inverse element, but every element I could find something in the negative side, which if I add that number to 0, that means to be an abelian group. That's one of the first property of what it means to be a ring. Then you have what we call a monoid and under the multiplication. So it is associative as well. And it has a 1, that's a unitary, that's such that you multiply it by any number, it will give you the same. And you have distributivity. So you can multiply with a sum and you get the sum of the multiplication. And the field, what will it be? So you can wonder, why would you pick Bose exact definition to be the definition of a ring. Why would we not extend? This takes a long time to think about it and to think about the independence of axioms and what makes something something and why is it relevant to look at this exact axiom. So I cannot answer right away what makes your axiom, but some mathematicians have thought about it for a very long time, and those actions are very special. And you can see that they were very special in my explanation all the time they came up. A field will be a ring, a commutative ring with unity, such that every non-zero element is invertible. So what if we try to interpret the multiplication of Q without the addition? Well, you will need to think about how multiplication works. And here we get back to the fundamental theorem of arithmetic, which tells you that every single integer can be written uniquely in terms of a prime factorization up to unit. And that's how you can think of a multiplication without addition. So the question we ask in the work we did with Leandro is that, is it possible to define a meaningful addition compatible with a multiplication? So more precisely, you take a field like R or C or Q, even a ring actually, you remove the addition and you ask yourself, is there another addition that I can put on this field such that I still get a field? And what can you say about that? What can we learn about that? And for the simplicity of the talk, we will remain with R and C as I have started with. So there will be only 3 slides, which are a bit theoretic. Then we will go back to simple. And this is the one step toward the answer to that question. If you take a multiplicative morphism, will define as addition, which make what I asked just now happen, and by this is addition. And this addition depends on the multiplicative automorphism of a group, and we found all the multiplicative morphism of R, or we didn't find them, already found before, known. And then we found those of P. We don't know if they were known before. We don't find it, so we found them. And Leandro will tell you what we did with them, which result we obtained.
Okay, so I'm not a cool kid. I don't use Mac, so Sophie has to see if this works. Yeah, I see that works. Okay, all right. So part 2. Numbers, addition, multiplication, etc. So for the rest of the talk, I'm going to, my children always ask me, what do you do for a living? I say many things, but one of them is showing you that 1 + 1 isn't always necessarily 2, which is what we're going to be showing in the next few slides. And it all follows from these notions. I just want to go back a little bit here. That these automorphisms actually induce these new additions given by these things. All right. So a few examples for the rest of I'm going to do 2 things. Partly just show you very simply how 1 + 1 isn't necessarily 2. And then I'm going to show you how potentially useful that can be. All right. 1 plus 1 doesn't have to be 2. You can tell your grade 1 teacher she lied. All right. Let's for simplicity, let's start with, I'm going to start with R. And just in terms of the previous notation, I'm going to denote this. I see what you mean, Sophie. It doesn't always want to work. Aha. My wife will not tell me, believe the woman. Escape. How do I get out of here? Believe the woman. Don't be clever. All right. Oh, now I need to do this. Okay. All right. I shall believe you next time. All right. Okay, so let's take two. Oh, so just a question on notation. So let's define this M plus. Remember in the previous thing we had this addition given by this induced addition, and this is just the automorphism. We're just going to simplify the notation. Just write it M alpha plus alpha. Okay, and for K, where K is just the general field for K being R, the real numbers. Let's take two simple numbers, M equals to 1 and N equals 2. And now we want to sum those two numbers. All right. For alpha equals to 1, we should know the answer is just 1 plus 2 is equal to 3. For alpha equals to 2, now this epsilon 2 is defined, sorry, I need to do this in this way. It's x squared if x is greater than 0, and it's minus the minus of x squared if x is less than 0. And then it's a very simple, it's just a plug and play. 1 plus 2 is equal to this little mess. This is just the specific application of the general thing we saw earlier. And it is equal to, so I don't know if you said this, Sophie, but 1 just maps to 1. And epsilon 2 here is, well, just plug it in there. We get 1 squared, so this is 1 plus 4 is equal to 5. And so 1 plus 2 in this new system is actually to the square root of 5. Okay. Told you 1 plus 1 isn't 2. Or 1 plus 2 isn't equal to 3. If if alpha is equal to 3, we have that the automorphism is just given by x cubed, and then the summation looks like that. All right, and it's again just a question of plug and play. And now we get to the cubed root of 9 for 1 plus 3, 2. And so we can go on. Alpha can, of course, be any real number here. I've just stuck to the integers, just the simple ones that we know and love. All right. Okay, so one more little example, just to drive the point, or some of us, at least for myself, point home. So if m is equal to 1 and n is equal to minus 2, then considering again alpha equals to 2, we would get the following. It's again just a question of plug and play. But if you go back to the definition that I gave you up here of for x squared, for alpha equal to 2, we get this. And so what I end up with is minus the square root of 3. And how do I get rid of these people over here? I can't. Okay. Sorry, you don't see that. Okay, so note that this is not the square root of minus 3. It is actually minus the square root of 3. Okay. Otherwise we would be breaking ourselves. We would not be on R anymore. Okay, and it wouldn't make sense. Okay, so all of this just follows from the definition of the automorphism. It's an interesting fact that, so what I've done here is just, it's not an interesting fact, it's just a fact. What I've done here is just plot, taken for a bunch of values of alpha, starting at 1 up to 7. And what you see is eventually this thing converges. You could carry on and on to actually the largest one of these two. So it was 1 and 2. And okay, in the previous case was 1 and 2. And I just find that the result eventually converges to the maximum. We actually proved that it will always converge to the maximum. And it's not surprising. In a certain sense. Okay, so now that we know for the real numbers that 1 plus 1 is not equal to 2, or 1 plus 2 in this case is not equal to 3, what does it look like for the complex numbers? Okay, so our, just a reminder here, our automorphism, this mapping for the complex numbers is simply if I apply this is messing with my mind, having to scroll with the fingers and to point with something else. If I take this epsilon alpha for some complex number z, then it's just the modulus to the power of alpha. I'll explain what alpha is in a moment, and it's just times the exponential times the argument of z. And the inverse is a little bit more complicated. It looks like that. Okay. And in this case, my alpha can be alpha here. I start with alpha. Alpha now can be a complex number. So Sophie showed you earlier that it can be a plus ib, where a and b are just real numbers. Okay, so let's start with the simplest case, where the alpha here. So I'm doing this now for the complex numbers, but the alpha, the exponent that appears in my automorphism, there is just a real number. Okay. Again, there's our standard definition, and if you look at, sorry, just need this and that, I'm just taking this and applying it here. I deliberately chose these two numbers, m equals to 1 plus I and n equals to 3 plus 3i, so that the argument is the same in both cases. That's just pure laziness. And so that we can just get this beautiful thing out here. Okay, and so no great shakes, we can add those things together. Oh, just one comment here. If alpha is just equal to a, so it's just there's no imaginary part to the alpha, then obviously the imaginary part is 0, and then this little mess over here is just 1 over the real part, which is what we have here. And so this, remember, every time I do this addition, it's a very simple little algorithm. I transform these numbers that I want to add them together with the normal addition that I love and know, and then just apply the inverse operation there. Okay, in this case, alpha to the -1 is just e to the epsilon alpha -1 is just this little mess over here. And no great surprises. If I said alpha equals to 2, all I would do is I just replace a there by 2, go through the motions, plug and play. And again, why these simple examples? Just to show you that we saw for the reals 1 plus 1 isn't 2, was 1 plus 2 isn't equal to 3. And now again, just here for the complex numbers, I should know, if I were to add these two things just normally without these funny induced additions, I would just get 4 plus 4i. But what I get is in fact something else. Okay, and just hang on. If this is all there is to it, then we are almost wasting each other's time. But just the punchline is coming. Just hang on. Okay, and so let's make things a little bit interesting. If I were now, I'm not going to do this in great detail. If I were to take those same numbers, this m equals to 1 plus I and through n equals to 3 plus 3i, but now I consider my alpha a little bit more general. The imaginary part of this alpha is now not 0. So it's just some non-zero real number. What I will get is the following. Again, I'm just applying the same little algorithm over here, and I get this little mess over here. You see, now instead of just a, I have an a plus ib. And just a little reminder for those in our midst that if I'm not going to go through all this, you all should know this. In fact, you all do know this. If I have this, I can write it as such. And so what I end up is, let's make a specific choice for a equals to 2 and b equals to 1. What I end up with is this little mess over here. Okay, again, the answer is different. I know. And Sophie and I had a bit of an argument yesterday, not yesterday, somewhere, about should I write this? I said yes. She said mathematicians aren't interested in this. Well, I'm not a mathematician, I'm a physicist. And the reason I want to show you that is just simply remember my little mantra: 1 plus 1 is not equal to 2. It's just to show you this. Okay. Again. Oopsie, what am I doing? I don't want to do that. Obviously, I skipped a few steps here in doing it. So the this is another point of contention. If it's tedious, put it on a computer. Just make sure that the answer is right. Okay. All right. So the point of just this first bit is to say, with these induced additions. So the question Sophie asked was, can we get additions from multiplication? And we can if we have these. We start with the multiplicative group, and we have the automorphisms, and we can induce these additions, and they are given in this form. Okay, and this is now for R and for C. I took the advice of my master supervisor. You would know him, Francesco Hendrik. He said, "Don't give a talk without a picture, because people like pictures." So I'm going to show you two little cool pictures and say a little bit about something about them. So one of the questions that we actually asking ourselves in all of this story is, okay, so in fact there are a number of questions, but one of them is, what are the, I was going to say, geometrical implications of what we are doing? Can one you know, we all know for the complex plane, I can, and the fact that I write here the argument over there, I can have angles and stuff. And so our question that we ask is, do things look differently when I go to these new systems? And the answer is yes. So what I want you to do is just look at these two previous cases very simply. If I have just alpha, where alpha is just real, we saw this. And the result is this. So in a sense, it's like only, you see the modulus was square root of 2, and now there's just a stretching of, it's like just I take the thing and I just stretch it a little bit, and the stretching is dependent on whatever the value of A is. If I have A plus IB, then I get this little mess. So there's like a stretching of the thing and a rotation. You see the argument is now different. It's changed by whatever B is and whatever the modulus was. And so the pictures, just to mess with my mind and everyone else's, is if I take the complex plane, just the complex plane, and I apply this transformation just for alpha equals to 2, I get this thing on the left-hand side. So there's just a stretching of everything. If I take alpha as 2 plus I get there's a little bit of a stretching, and things start twisting a little bit. And we're still thinking about what all of this means, but I just needed to show you these little cool pictures. Now the picture that's really going to mess with my mind, it felt as if I sat in a washing machine. It's that. It's like I drew these pictures and it was like, whoa, we're in the washing machine. And what I did here was just to undo that little mess a little bit. So we start with the normal complex plane. You know, just everything is nice. I deliberately colored I don't know if you can see that the vertical lines red and the horizontal lines black. And if you do just take these things apart, what you see is those beautiful horizontal lines transform to the thing on the left, and the vertical lines to the thing on the right, if alpha is 1 minus 4i. Okay, so that's still ongoing work. We still, so there was a twofold point of adding this little picture. One is up till now, just to convince you that 1 plus 1 isn't necessarily 2, and the same holds for the complex numbers. 1 plus 1i is not necessarily, you know, it's not, 1 plus 1 isn't 2, whether it's real or complex. And here, the point was simply to say, listen, if we do these transformations, even the complex plane itself starts turning into something interesting. We don't quite know yet what. We're still busy scratching our heads around that, but it is quite interesting. Okay. Now, so if 1 plus 1 isn't always equal to 2, then my grade 1 teacher, who happened to be my mother, lied to me, and she wouldn't want me to tell her that she lied, but she did. But there's usefulness in the 1 plus 1 not equal to being 2. Okay, so where does all of this, as we were doing these things, we discovered that these additions of ours actually are very reminiscent of things that appear in statistics or classical sort of power means. You know, sort of the quadratic mean, the what's the thing called? Geometric mean, and all of those things. And they are all, I'll show you in a moment, they're all just special cases of a very more general thing. So these induced additions by these multiplicative automorphisms allow us to define an extension of power means. So what are power means defined for? They're only defined for the positive real numbers. Okay, and so what we find is these additions of ours allow us to extend that notion for, let's call them data sets that include negative numbers or mixtures of positive and negative numbers, and even to the complex numbers. How are we doing for time? 16:41. Okay. And so the basic, usual definition of the weighted power mean of a bunch of positive real numbers, let's say Rj with weights omega j, is simply this. Okay, where we just wrote here the positive real number and its associated weight, and it's just this thing. So it's basically the weight, sum over all these numbers times the weight times the number raised to the power of alpha, the whole thing to the power 1 over alpha, where alpha is some real number. Of course, this is, yeah, any real number. And what we discovered is if we, so the slide this is towards generalizing these power means. So if we take these weights and we write them in this little interesting way as a sum of complex exponentials, so some e to the I theta k and its complex conjugate, where this theta k is actually determined by the weight. Okay. What we find is that we can rewrite this usual thing in terms of these summations of ours, where all we do is we define this notion of ajk, where it's the number times this thing that is proportional to the weight. And k is plus or minus 1, j is all this runs over the set, and then I can write them in terms of this new addition, where, remember, this is not just the addition that we defined previously, these induced additions. So I can actually, I'm not going to go through all of these steps. The important take home is I can write this power mean, the classical, the stock standard power mean, I can write in terms of some pair of numbers, but added with this, where the addition is this induced addition, this plus alpha. That's the take home for this. Okay, you can go through these steps here, but I don't think that's important. The point is just I can write these ajks as this number that I'm interested in, this e to the I k theta j, where this is just proportional. It contains the information of the weights. Okay. And take home is I can write this normal classical power mean in terms of these new additions. And we can, using exactly the same procedure, all I do now is, we all know if I were to write, for now, I'm just assuming alpha is real. We did the whole thing for any alpha, and it's quite messy, but what I've written here is just the real version for alpha real. If I simply write my data points, let's call them that, in this way, well, there's nothing new here. Well, what will I get? If it's all positive numbers, the arguments will just simply be 0. If it's all negative numbers, the arguments will be pi. And anything in between is, if I have anything in between, it's just a mixture. So going through that same procedure that I didn't run through, but just mentioned over here, the same story, where the take home was this power mean can be written in terms of quantities that I add with this induced addition. What I can find is this, I can find a generalization of this power mean which is now given by this. And it's again just this epsilon. It's you can see it's all in terms of the induced additions. Okay, so that's the take home of this. So these funny additions, let me go up and add one more bit. These funny additions that we started off with, where 1 plus 1 isn't equal to 2 necessarily, they allow us to do the following. We can write down a more general form of these power means that are not just defined for positive real numbers, but for also things that include negative real numbers or even complex numbers. That's the take-home message of this story. Everything, like the usual case where all the RJs are positive, is just recovered when the arguments here of all the RJs are 0. I've just said in principle, which is what we did, we can extend these things to complex valued alphas and weights, but we're still working on what all of those things mean. Okay, so 1 plus 1 isn't necessarily equal to 2. And you could say, but now why is that important? Well, it's important because in the cases where 1 plus 1 is not equal to 2, it's because we have a different addition. And this addition is induced by these automorphisms. What was the usefulness of this? Those very same additions allow me to extend the definition or not the definition, to extend the concept of the power mean or generalized mean to numbers that are not just positive real numbers, but I can include positive and negative and even complex numbers. Okay. And so, again, we had an argument. No, we didn't quite have an argument. One would think Sophie and I only argue. Healthy debate, let's call it that. About just a simple example, and there's a reason I put this little slide up here. So if I have 4 numbers, 1, 2, -8, and 10, and I want to calculate. This is just for the reals now. I want to calculate what is their power mean for any specific alpha. Well, it's just a question of plug and play. I do this. And what I did over here was I just plotted this for a whole bunch of alpha values up to alpha 40. Alpha is just real now, up to alpha 40. And an interesting thing, I mentioned this briefly earlier, but we actually proved all of these things quite formally, but we weren't going to. Francesca already said the title hurts your head, so if I were to throw that up, it might have hurt your eyes too. Remember, for the power means, generally, if I take alpha going to infinity, the result of that mean is just the maximum of whatever is in that set of numbers that I'm adding or calculating the mean from. We go alpha to -infinity, it's just the minimum. This is not a proof, this is just almost evidence. We did actually formally prove this, that in this case, as I'm increasing alpha, I should expect that this mean should tend towards the maximum. The maximum in this case is 10, and it does actually. I just stopped at 40 because I think the point was clear. But so the point of this is just to say that all of the properties that we expect of these power means actually also carry over to these more general versions that we have defined over here. So that is the story for today. So in a sense, to conclude, we've taken you on a journey that started with the numbers. And the central question was right sort of towards the end. Sophie's question was, can I get addition from multiplication, essentially? The answer is yes. And it's given by these funny additions induced by the automorphisms. And then the story was just very simply to show you 1 plus 1 isn't necessarily equal to 2 if I'm working with these new induced additions. But it also has potentially usefulness in that it allows us to define these more generalized power means that extend the possibility of computing these things for data sets that are going beyond just positive real numbers. And that's our story. Thank you very much.
Yeah, thank you very much for the very interesting talk. Other questions from the audience?